Hey there, let's talk about rotation types in an AVL tree, which is a self-balancing binary search tree. Okay, so hopefully you've watched my previous videos. If you have not, you probably want to check them out first, where we talk about what is a binary search tree, how to build one, how to define one, terminology, searching through it, all that stuff. And then we talked about an introduction to AVL trees, which are self-balancing binary search trees. This video is going to be about the types of rotations that you can perform in an AVL tree. What do I mean by rotation? Well, the basic idea that we talked about in the last video was that throughout your tree, you'll notice that different nodes have different balance factors, which means how imbalanced or balanced they are. When we identify a node that has a balance factor that's too bad, then we consider this to be an invalid AVL tree, and we have to stop and rotate a couple of nodes, kind of rearrange them to make them better before we have a valid AVL tree. So we have 4 different input patterns that we can have. So imagine, this little trinode subtree up on the top left. That could be, 3 nodes that we found somewhere in our tree that had a bad balance. If you just quickly compute the balance factor for this trinode subtree, you'll notice, actually, let me just do it real fast for fun. You'll notice that the 65 node has a balance factor of 2 because its left subtree has a height of 2, and there is no right subtree. The 55 has a balance factor of 1, and 48 being a leaf, at least in terms of this trinode subtree, has a balance factor of 0. All of these trinode subtrees are going to have the same situation. The one on top is going to be 2, and so forth. So you can imagine that you were going through the whole tree, computing balance factors like a giant tree, and you found a 2, which, remember we said in our last video, 2 or worse, meaning 2 or higher, if we're using balance factors that are absolute, or -2 and also +2 or worse, if we're not using absolute balance factors, means you got to stop and try to rebalance that trinode subtree. So we found a node that had a balance factor of 2, and we realized we have to stop and rotate. The pattern of the trinode subtree before we perform the rotation could be one of these 4 things. It could be the thing on the left on top, the thing on the right on top, the thing on the bottom left, and the thing on the bottom right. And all 4 of these patterns should end up becoming, after we do our rotation, they should end up becoming the pattern in the middle. So this is always going to be the target pattern. Let me draw some arrows real fast. Every single input pattern is going to end up looking like the output pattern in the middle. Why is that? How is that possible? Well, we only have 3 nodes. If you look at all the input patterns, they're all the same numbers. What we're really doing is disconnecting all the pointers, disconnecting the parent-child relationships, and then reconnecting them in the best possible way to make, the most balanced trinode subtree. Notice how the height of all of these input trees is always 3, right? Because it's a trinode subtree that's really, really bad and out of whack. So we'll, like 1, 2, 3, 1, 2, 3, right? Height of 3. We'll do a rotation, rearrange the pointers, rearrange the parent-child relationships, so that the final height ends up being actually just 2. And if you think about reducing the height, we're making the tree better. We're making it more balanced. We're making it faster to search through and add and remove things from. So we're making a better tree by reducing the height a little bit. If you had a really, really, really bad tree and you just went around to all the bad nodes and just started rotating them all, you're reducing the height by 1 for each rotation. Eventually, when you get up to the top of the tree, you'll have an overall AVL tree, which is pretty fast. We should say now that AVL trees are always going to be log time trees because the imbalance factor is limited by a constant number. We'll say that again in a future video. So anyway, I'm going to label these trees now. I'm going to say that the one on the top left is a single right rotation. And the tree on the top right, you can probably imagine, is a single left rotation. Let me just duplicate this real fast so I can edit. Come on, man. Can I duplicate this? Yeah. So I can just edit the text real fast. This is going to be a single left rotation. And then the trees at the bottom, those are going to be double rotations. Let me just write over here, maybe next to that one, double right rotation. And then I'll duplicate this. And this one over here is going to be a double left rotation. I placed these on different sides than I usually do because I was trying to make it look a little more tricky, but it's really not that bad. So how do we know that the top pattern is a single right rotation and not a double right rotation, or it's a single right rotation and not a single left rotation? The first thing to try to understand is what's going to happen between the input pattern and the output pattern. So if you look at the input pattern here, we've got like a straight line, and the output pattern is like a perfectly balanced trinode subtree. Notice how the 55 is the new parent, and it's also in the middle for the output pattern. And then for the input pattern, the 55 is also in the middle, but it's not the new parent. But it is the parent already of the 48 node. Notice how it's the parent already of one node, the 48 node. So that means its relationship to the 48 node, the left child, doesn't actually change. So if you kind of think about it a little bit more, you'll realize that only one node actually needs to be moved into position. So we'll call this a rotation. Try to imagine, visualize maybe like your left pointer finger being placed on the 55 node and your right pointer finger being placed on the 65 node, and then just rotate the 65 node downward. We rotate that clockwise, and the physics people out there love to say that clockwise rotations are right rotations, at least as far as I remember. I'm not totally sure about that, but I'm just going to say it anyway. So notice how the 65 needs to be rotated to the right or clockwise, and only one node actually needs to be rotated to produce that final output pattern. That's why we call this a single right rotation, because there's only one node to rotate. The next thing I'll do is just try to give you a few extra ways of being able to remember whether it's a left or a right. So for starters, one node needs to be rotated, so it's a single rotation. And we're rotating clockwise, so it's a right rotation. But you can also do this. You can think of it like, can I get rid of that real fast? You can think of it like, well, there is a bunch of empty space kind of sitting here on the right side. So that could be another way to remember that this is a right rotation. Also, if you were to start at the node in the middle and work your way to the node at the top, the Z node, then we're kind of going up and to the right. So that's another way to remember that this is a right rotation. Single, you can remember that also by just the fact that this is a straight line. Like notice how the nodes are kind of in a straight line. They don't do a zigzag or a bounce. So single rotations are rotations that look straight at first, or I guess input patterns that look straight, and only one node actually needs to be rotated. Right versus left is there's a pocket of empty space on the right side, and you go up and to the right for the right rotations. Similarly, you can probably already figure out by now that the left rotation just means, well, we're going, we're going up and to the left to get to that top node. Or the only node that has to be rotated is that 48 node, and it's going to be rotated counterclockwise, which is left. So again, only one node needs to be rotated, and we're going to rotate it counterclockwise, which is a left rotation. So one node rotated, single, counterclockwise, left, or just like a pocket of empty space sitting on the left side. Okay, so then for the double rotations, the first thing you can look at is the idea that there's a little bit of a bounce. There's like an angle bounce there. If you see a bounce or a diagonal, sorry, I was sick a couple weeks ago, then that's a double rotation. Another way you can try to remember it as two nodes need to be moved into position. So if maybe I should copy this to another slide real fast. Let me copy this and we'll do another slide. Okay, so, which nodes need to be moved into position? Let me copy also the output pattern just as a quick reminder. If we wanted to make that output pattern, let me put it up here maybe, then obviously the 55 still has to be in the middle because it was already in the middle before we rotated. That means both the 48 and the 65 need to be rotated underneath the 55. So that means we're going to do the 65, we're going to rotate it clockwise underneath the 55. So I'm going to do like a little circle here, a connector, and then I'll do like 65 there. And then after we do that rotation, we have to rotate the 48 underneath the 55. So that's going to be a rotation that is counterclockwise. So I'm going to do this, Circle that there, and then do a 48. Notice how when we're done doing the rotations, we have a valid binary search tree. You should always check your rotated pattern, your output pattern, to make sure it's actually in order and it's a valid binary search tree. Because if it's not, let's say the numbers are out of order for some reason, from left to right, then you have rotated incorrectly and you have to double check yourself. So 2 nodes need to be rotated into position, therefore it's a double rotation, or you see a diagonal input pattern, double rotation. How do you remember the difference between left and right? Well, if you start at the node in the middle, just like we did in the last slides, if we start at the node in the middle and go to the node at the top, the Z node, we're going up and to the right, and so this is a right rotation. So it's a double right rotation. Another way to remember it is you should probably try to rotate the Z node first. The node that's on very top is the 65. Rotate that first and then call that the direction of the rotation. So, we rotate the 65 first, that's a clockwise, so that's why it's a right rotation. Then just ignore the direction of the other node that you rotated. You can also kind of imagine taking the original node. If you don't want to think of like actually rotating, let me just kind of erase this real fast. You can kind of imagine that you are, you're sort of taking the new parent that's supposed to be the new parent and just sort of pulling it up. Sometimes when I teach this to people, I draw a picture of Batman and he shoots a batarang at it and he sounds like Christian Bale and he's like, "Where is the rotation?" I'm not going to do that. Maybe if there are enough comments, I'll do a special video just for my really, really bad drawing. But imagine the 55 is getting pulled up and it's getting pulled up past 2 other nodes. So that's why it's a double rotation. Another way to remember. The 55 would be the mob boss that's hanging by his ankle. Anyway, so we kind of know how we can remember the difference between single and double rotations. We've got a single right rotation, a single left, a double right, a double left. There's only going to be 4 possible input patterns, and they're all going to look like this one output pattern, because really what we're doing is we're not, creating any nodes or removing any nodes. We're just disconnecting pointers. We're disconnecting the parent-child relationship. We're saying, let me just get this over here. We're saying, okay, input pattern, I disconnect the pointers. I'm saying the 65 no longer has a left child, the 48 no longer has a parent, the 55 no longer has a parent, and the 48 no longer has a right child. And then when we're done with that, we just kind of like reconnect the relationships. We're like, okay, you know what, just kidding. You all have parents and children again. We're just rearranging them. Okay, let me check out my thing real fast here. So I'm going to cut the video here because this is the basic idea for the different types of rotations that you could use. In the next videos, we're going to actually start rotating bad trees to make them work. So thanks for watching this video. I hope you learned a little bit of stuff and had a little bit of fun. I'll see you in the next video. Okay. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. Sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? Just send me a comment. Whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness, which is coming for us all. Hello there. Let's talk about rotation types in an AVL self-balancing binary search tree. Nope.